So again, I'm Dan. So today I'm going to take the opportunity to talk about some of the issues we're facing in the electric machines space. And then originally in the abstract of this talk, I was going to talk about two paths my research is taking in electric motors. But when I made that presentation, it wound up about 2 hours long. I'm going to get 1 hour. So I cut it down to one, but I will mention high-level aspects of the other path. So, all right. So one thing I'm going to touch upon a little bit. We'll go through a little bit of review and motivation behind electric motors and their physics, and then delve into my work. So we don't call them generally motors or generators in the power conversion trade. We usually call them electric machines. It's a catch-all term because, oh yeah, I forgot I lost my animations. But if you put electricity in, you get motion out. You put motion in, you get electricity out. And I'm sorry, I've deprived you of the cute animation of where the arrows flip direction. But so a motor is a generator, and a generator is a motor. Just depends what way you're putting power into it. Okay? And they're everywhere. They're ubiquitous. So they're in aircraft. They're in your electric vehicles or hybrid vehicles. This is a big industrial chiller that keeps us all nice and cool in summer. They're in wind turbines. They're everywhere. So 99% of all electricity comes from a generator, an electric machine. And all of that electricity, 2/3 of it, roughly 2/3 of it in industry and about 46% of the whole grid goes to powering an electric motor of some kind, doing work, whether that's pumping, grinding, transportation, you name it. So 46% of the whole electric grid goes to motors. 2/3 in industry, subset of the grid. All right, so how do we get force from electricity? So this is bringing us back to physics in high school or your physics in the first part of your college career. So this is just some basic magnetism. This is our familiar Lorentz force with the right-hand rule. Who here remembers their right-hand rule? Anyone? Few of you? Yeah. So it's always fun when we give tests on the right-hand rule because students are looking down at their paper and they're like making weird symbols with their hands in class, and it's always kind of a joy to watch. But very simply stated, if you have, these are the poles of a magnet, north, south, you have a filament of current going through that gap. The magnetic field cuts across. This is magnetic field B. You have current, so you have I cross B. Thumb points out in the direction of the force, which is, in this case, out of the stream. And so that's denoted here by this cross product. The integral goes over the length of the wire. In this case, this is more representative of what you would see. This is what I like to call the refrigerator magnet. You have a magnet, you put it in the vicinity of some permeable piece of metal, iron, for instance, it's going to stick. And so in this case, instead of being a permanent magnet, it's an electromagnet. And so this is a macroscopic representation of this occurring at a microscopic scale. But you have a certain amount of field energy, and it's just a natural principle that to minimize this path for this energy follows a derivative here in space. And so if you were to write a function for the energy stored in this air gap and take its derivative with respect to position in this direction, that would give you the force in that direction. So this is what's called a reluctance actuator. This is like a solenoid, things like that. Put a current through it, it sticks. This is called a Lorentz force actuator. It's a cross product. Okay, these are the two basic building blocks that we use in most motors. So the first person to demonstrate these, more notably the Lorentz force, was this handsome man here, Michael Faraday. This is 1821. So in a few years, 4 years from now, we'll have the 200th birthday of the electric motor. Okay. And what he had was this interesting contraption you see over here. These are cups of mercury. And this is a wire that's going down into the mercury. This post here and here, these are permanent magnets. And he found that when he dipped the wire into the mercury and he ran a current through them, into the mercury and out through the bottom with a battery, he would make these wires orbit the magnet or make the magnet orbit the wire in a circular motion. And so this is the first demonstration of putting electricity into something and getting continuous motion out of it. And so that's why Faraday is credited with inventing the electric motor, even though this is nowhere near anything that you could use to do work. That roughly showed up about 5 to 10 years later. This is another diagram you might be a little bit more familiar with. So this is the basic DC motor. Okay. Works off the Lorentz force. So in this case, if I have a battery here and I have current flowing up through this wire, through the brush, up through here, through this coil, back across and down around, as the magnetic field from these permanent magnets crosses this coil, I have an I cross that with a B, and I get my force, which is vertical. And so if I have a vertical force at a radius, I'm getting a torque, okay? And when the current comes back across, and it's in the opposite direction now, so the force is down, and so these two torques add. And so the torque generated by this type of motor is a function of the current through the wire, the length of the wire, the radius that it occurs at, and then the strength of the magnetic field that it's immersed in. Okay? And so as this coil experiences a torque and it begins to rotate over, notice this is a cross product, so you have the cosine theta comes into play here. And also notice this thing's called a commutator. This commutator ensures that as the coil flips over, eventually, this positive current, if I were to just have a direct connection to it, would then be going this way, and I'd get a torque, so it would just oscillate back and forth. You could not get continuous unidirectional torque. So these brushes and this thing called a commutator ensures the torque is always positive. Okay. So to control this thing, we control the strength of the magnetic field by selecting the magnets we want, and also the strength or magnitude of the current that we put through this wire. So note those two things. So that's a DC motor. And then this is also a DC motor. This is a cross-sectional view of one where instead of permanent magnets, we have poles that we wrap wire around to make an electromagnet. And that way, if we put the current through that coil on the electromagnet, we can control the strength of the magnetic field. Instead of having just one loop of wire on the rotor, we put more, and we put more taps on the commutator. That reduces our torque ripple. So for a DC motor, the armature winding, which is on the rotor here, and you have the permanent magnets or the electromagnets on the stator, like so. For an AC machine, we flip it inside out. We put the magnets on the rotor and the coils on the stator. So in this case, it simply allows us to have, so these work on the exact same principle. You want to put current and flux at 90 degrees to each other. In a DC motor, this orientation of current and flux is maintained by the commutator. So as these coils rotate, it is always ensured by constantly moving on these taps that the current is always going in the right direction. For the AC machine, it's done electronically. We put AC current through these windings to always keep the current in the same direction with respect to the magnet. So as these magnets go around, we always change the current in the windings to track the magnet. That's electronic commutation. Okay, instead of this is more recently developed, in the last 30 years or so, because that's when electronics became good enough for it to work. And so DC motors are going the way of the dodo slowly. Because this thing, this commutator, wears out. It's brushless. It's a mechanical thing. It's a mechanical contact. It's going to wear out and go away. And so AC machines, which are what are in all of our electric and hybrid vehicles, have benefited largely from power electronics and also really cool magnets that are very powerful. One of our faculty members, Tom Johns, who's no stranger around here, is a pioneer in these brushless AC permanent magnet machines. And that was some work he's pursued throughout his career. So at the end of the day, though, if you're just looking at this, you need current, you need flux. Flux comes from magnets, the current's carried by windings. And then you've got iron. The iron's there to get the path of the magnetic field short and with low resistance. So you can use every last drop of these magnets. Right? So this is what a state-of-the-art AC permanent magnet machine looks like. This is in General Motors Chevy Spark. I'm a big fan of this motor. And it's got hairpin windings on the stator made out of copper. And they have an interesting design that allows them to spray oil directly on the end turns to cool it, pull the heat out of this motor. And then this rotor here is filled with neodymium iron boron magnets. And a motor like this is about the size of a watermelon and over 100 kilowatts. Okay. Far more than that, actually. So this represents the state of the art. We got steel, neodymium iron boron magnets, and special copper windings. All right. So what are the motivating factors in electric machines today? We want lots of torque. Because when you buy a machine, you pay for torque, because the copper, the magnets, and the steel size how much torque you get. So that's torque density. Power density is interesting in that because power is torque times speed. So if you can actually have a very low torque density motor, but if you let it spin ridiculously fast, you can get high power. So that's another. So depending on your applications, aircraft generally like small motors because they're lightweight, and so they let them spin really fast to develop their power. That's whereas where you want more torque is generally a variety of applications. They can be in robots or traction drives, all sorts of things. Wind turbines would love a direct drive. The gearbox that you typically use to scale the torque of an electric motor is a mechanical thing that's prone to wear or failure. So this is an active area of research, is creating low-cost direct drive motors. Efficiency, cost of operation, system impacts, how long will it last, environmental hazards, heat, dirt, water, vibration. And then this one, material costs, supply chain, availability, labor costs for making the thing. Can you automate all of this? Okay. So if you're making a lot of motors, you can automate it. But if you're making lower volume motors, it's still largely done by hand. And isn't it look like a fun job? So this is it's an art form, winding a machine. And so you can automate winding machines if you have sufficient volume. But the conventional machines that I build in my lab are all done by hand. And a lot of mom and pop shops still around town for rewinding and rebuilding motors. So also, only the portion of the copper that's inside the iron does anything useful. But you can't just make the windings magically stop here and then reappear here. They have to come out, come around, and these are called end turns. They're a necessary evil. the accountants hate them because you're like, we're paying for all this copper, but it doesn't do anything. It's also the same sort of argument when you have to tell an accountant that you also have to pay for imaginary power. They don't like that either. So what else is in these magnets or motors? I just gave away my punchline for this slide. Rare earth materials. So this is a plot of price versus time for neodymium. And it's a neodymium iron boron magnets are in our wind turbines, they're in our hybrid cars, they're everywhere. And so people panicked because the price went up just a little bit in 2011, 2012. But since recovering, it's somewhere in here now. But it was cheap, and then China realized everybody wanted it. Then came up. But this is the core ingredient for our super powerful magnets that we put in all of our electric motors. And it's kind of fun to see how this is, at the time, electric motors became big news. Toyota was trying to get out of rare earth magnets. New York Times was reporting on making motors without these rare earth magnets. And there's other articles more recent. And so now it's become a real thrust in the academic community to try and eliminate these rare earth magnets from motors because they're a big bottleneck. This is copper. Copper has been going up considerably, somewhere in here now, but it's significantly expensive, right? Steel is very, very cheap, but copper and magnets are not. And so we need to use copper because these motors, you push current through motors, right? And if you're pushing current through a motor, the only naturally occurring element that has a better conductivity than copper is silver. And I don't think we're going to be making motors out of silver. Maybe in some fancy NASA outer space application, but for everyday use, no, they're not going to be made out of silver. So this is a cool plot of periodic table, and that the availability of these elements and over the next 100 years is highlighted a serious threat, rising threat from increasing use, limited availability, risk to future supply, and abundant and no information. So what are electric motors made out of? Well, you got steel, that's mainly iron. Hey, that one's all right, green. Okay, what about copper? Okay, so copper is not in too bad a shape, but it's still, as we saw, copper prices are over time going up. Everyone wants copper. We need this. Our magnets. So we've got a few different ones. Well, let's have a look at our neodymium iron boron. Here's neodymium. That's too bad. And then we've got, oftentimes, and this isn't stated in their name, but neodymium iron boron magnets use the element dysprosium to enable their operation at higher temperatures. And so there's dysprosium. That one's also there. You can also use weaker magnets. You have things like samarium, cobalt, things like that. You've got, here's cobalt, samarium. Those are endangered. And there's also things like ferrites and others, but they're lower performance. And so now the quest is on, all right, so our super high performance electric machines that we stick in all of our wind turbines and our cars and our aircraft are being made with elements that we're currently, running short on, or have significant volatility in their markets at least. Also, these rare earths are really hard. I shouldn't say they're not really hard, but they're they're not exactly good for the environment. If I go back a couple of slides, these rare earth mines are among the worst polluters and have serious environmental impact. And so there's a lot of pushback in some parts of Asia about increasing it. All right. So what can we do to fix this? That's the question. And so being a professor at a university, I see this as an opportunity to do something risky. Because, you know, if you're a major corporation, it's hard to try super risky things because, you know, you have to stay afloat. Whereas if I try something really risky in my lab, it doesn't work, but my student still gets a doctorate out of it, right? But this is the idea. Let's do something risky. So there's two tracks that I'm taking in my lab to solve this issue. I'm going to talk about the super risky one. The other one is less risky, but it's also really cool and it works well. And there's we were testing it in the High Bay lab here in the Wisconsin Energy Institute. So there's some lower risk options. Say I want to get rid of these magnets. The magnets are the worst part. Let's get rid of the magnets, the permanent magnets. What if we use electromagnets? Get rid of the permanent magnets. Let's use an electromagnet. The problem is that if I put electromagnets on a rotating rotor, how do I power said electromagnets? I would have to bring brushes back and slip rings. But we don't want brushes and slip rings because that is a huge reliability hazard and issue. And so no one wants a wind turbine where you have to increase the downtime periodically to service this thing. We need to get every last drop of performance out of that. Same thing with electric cars and other things. So my other path, which I won't be talking about today, but if you'd like to know about it, please talk to me, is wireless power transfer to power these rotating electromagnets. And so the same types of technologies you see for iPads and phones and laptops and things, I use to power the electromagnets that are on these spinning motors. And so now it's just copper and steel. There's no more rare earths. Oh, dropped my pointer. All right. And there's a good survey paper on the lower risk approaches, as I call them. Here, it's not my paper, but it's a good survey paper, and it's open source, which is why I included it. Okay. Other approaches are the chemists are trying to get the same performance out of magnets, but utilizing different chemistries. All right. So what if I want to make a fundamental materials change? I don't want steel, I don't want copper, I don't want magnets. I want to get rid of all of it. I also don't want windings. I don't want end turns. I don't want any of this stuff. So what am I left with? Pretty much a shaft. But there's a saying a friend of mine has, and that is, if you want something as cheap as dirt, you better start with dirt. And dirt usually leads to plastics or the like, or some other ceramics maybe. So these are low material cost. And also for conductors, what if I wanted to go from copper to, say, aluminum instead? It's cheaper and far more abundant. So if I can make a motor out of, you know, aluminum and plastic, that might be interesting. Plastic, you might say, that's terrible for the environment. But the one thing that it has going for it is I can go dredge stuff out of the Pacific garbage patch or down in my local recycling center, and I could make an electric machine using completely recycled parts. And when I'm done with this electric machine, I can send it through the shredder and turn it into something else, hopefully. Okay. All right, so plastic isn't magnetic. So what's it good for? And also aluminum doesn't carry as much current as copper does. So what do we got? We'll have to, maybe we can use an electrostatic torque mechanism instead. So instead of using magnetism, let's use the force that is the static cling for clothes when you take them out of the dryer. But But electrostatic motors aren't practical. Who here has ever used an electrostatic motor? Anyone? No. There's a reason. And so solving that problem has been the focus of my NSF career work. So it's high risk, but potentially high rewards. This is actually the very first electric motor. And it wasn't Michael Faraday. It was uniquely American by this guy here, Benjamin Franklin. And this was his electric carousel in 1748, 73 years before Michael Faraday. And so a lifetime. And his motion, he would rub rabbit's fur and charge these Leyden jars and then get this carousel of thimbles that he stole from his mistress he put together and got it to spin. And so he called it the electric carousel. So the electric carousel never went anywhere. But why? So since I'm giving this, I want to give a shout out to people throughout the history since Ben Franklin who have tried to make electrostatic motors. So Tesla, he tried, he did some work in it. Thomson, Van Graff, John Trump, ironically our president's uncle, Noel Felici, James Melcher, Oleg Jefimenko, Sanborn Philpin, and Richard Post. So this is some work by Dr. Jeff Lang at MIT in 2005. So anyone here heard of MEMS? So MEMS are these micro electromechanical systems. There's a rush to make these tiny motors. And it's very hard to make windings really tiny. Can't do it really. And so they made electrostatic forces. So they put voltages on these tiny little conductors here, and then that static cling drags a rotor around in a circle. And so they were going for making a 900,000 RPM motor that was 4 millimeters in diameter and 90 volts. And so this was intended to be a micro gas turbine to be paired with a micro system for, this was a DARPA project in the early 2000s. A little more recently, this is by the Shinsei Corporation in Japan. This is a 100 watt motor, 10,000 RPM. It needs 100,000 volts to operate, and it has to be in a vacuum. But it does spin. And it works by static repulsion and attraction. As you can see here, the positive charge flees the other positive charge and is attracted to the negative charge, and then there's a commutator here that switches it. This is the motor here, and then this is all the stuff around it to power it. So this is some work done by GE in the 70s. Their idea was to make large electrostatic generators using rotating plates. And they have this stack up, it's a voltage ladder, voltage multiplier using variable capacitors. And this was going to be 200,000 volts, 7 megawatts, and 10,000 RPM. And at that scale at the time, all of this still has to be in a vacuum. The problem with putting a shaft into a vacuum is maintaining a good vacuum seal for a shaft exiting a vacuum chamber. And if anything gets inside that vacuum, you'll have a breakdown event and this thing will destroy itself. That's always been kind of an issue with electrostatic motors, is you need really high field strength to make torque. And to do that, you put high voltage on something, and in open air, things break down and you get arcs. Okay, this is a follow-up, and more recently in 2009, that was done in the UK, and following up on GE's work. And so there's some people, this is starting to come back, but what is holding it back? So this is and here's magnetism, which we already talked about. and here's electrostatics. So if I have some charge and I throw an electric field across it, it's going to move in the direction of the electric field. And then this is similar to what I was talking about up here. This is a force where I'm trying to pull some dielectric material into between two plates, and it's dependent on the derivative of stored energy in the field with respect to position. Okay. So this is the electrostatic joules of magnetism. So, all right, I'm going to skip a lot of this math, but for those of you who like the math, we can use some of Maxwell's equations paired with the Lorentz force equation, do a few steps, and get a little bit more elegant description of electrostatic and magnetostatic forces. And so we're going to have something called the Maxwell stress tensor. And so this is an equation and has these terms. And these terms describe, depending on what these subscripts have as, elements of tensor. And so, for instance, if I was to assign two Cartesian coordinates, x, x, y, z, z, the diagonal elements represent pressure. So if I have a field between two surfaces, there will be some pressure. And then for off-diagonal elements, there are shears. And so this will make a little bit more sense if I look at this picture. So this is a generic motor. There's something that spins and there's something that's stationary. The function of all motors is to have stuff here and here that makes a field that goes this way in the air gap and this way. So for magnetic motors, it's windings and iron and teeth and slots, and it makes field components like this, and you get torque, force. Electrostatic machines, there's something else. And so actually, when we design electric motors, we actually start with these fields sometimes and work backwards. Okay? So if I look at the shear components, so electric shear, magnetic shear. So electric fields in air break down around 3 kilovolts per millimeter. That's where you get arcs and sparks and things. So if I have voltage between 2 points, so if I have that, let's say they're a millimeter apart, if I put 3,000 volts on that, it will arc over at that point. That's the breakdown strength. Magnetism doesn't have that. I can make a field B as large as I want. Air is not going to do anything. The bottleneck for magnetism is, can you cool the windings of whatever you're using to make that field? So it turns out that in open atmosphere, you can get roughly 1,000 times more force per unit area or shear than electrostatics. So if I was to make a motor in open air, the surface area of the stator and the rotor would have to be 1,000 times larger than the magnetic motor for them to have the same torque, which is why we don't see electrostatic motors in the world. So I want to solve this. So what do we do? So the people at MIT largely focused on putting everything in a vacuum. Same thing with GE. This is a royal pain. You could also, some other people like Noel Felici describe filling the machine with an insulating gas at high pressure. That's like thousands of PSI. That's hard. So your motor becomes a bomb. So you don't want to do that. And so I'm proposing this option. We live in an age of marvelous new chemistries and liquids. Why not try filling it with a liquid instead? So this is the space. So if you want to make torque and your speed, vacuum allows you to go way up in speed, but you don't make much torque. Gases allow you to be in here. And my approach is going to be this: it's a liquid. we're going to be limited in speed, but most of the time, electric motors, like magnetic ones, aren't so good at low speed anyway. So this is a good entry point, is to make something that's great at low speed. Okay. All right. So this could be paired with things like robots where you have to position and hold, or low-speed wind turbines, things that spin slowly. Okay. I don't want to make this thing out of crazy materials. I want fairly off-the-shelf stuff that isn't very harmful. And we need to develop the tools to do it. This is my graduate student that's working with me on this project, and I wanted to acknowledge him because you know, he and I are doing this together. All right, so magnetostatic and electrostatic. In this case, they're very similar. So inductance of a motor is the flux over, some current. In this case, the capacitance of the motor that I'm going to build, because this is electrostatic, is going to have some sort of electric flux or charge divided by voltage. And so if using the well-established rules of designing motors based off of what are called reluctance equations, magnetic circuits, I can extend the same thing over to electrostatics. And it turns out there's something called elastance that is the dual of reluctance. So reluctance is the opposition of a path to the flow of magnetic flux. Elastance is opposition to electric flux, okay? In this case, charge. So I want a liquid. And so we went and we looked all over at all the different kinds of liquids, and we started to, well, let's look at some oils, some vegetable oils. FR3 is another vegetable oil. DuPont makes this stuff called Bertrell. We've tried that as well. So we decided to try these things. These we didn't try because they either won't work or were dangerous. Also note that everything here from an MSDS perspective is all ones and zeros. So we had to make a thing. What is the thing? It is a test stand to measure the pressure based off that Maxwell stress tensor equation I was telling you about. How much force can we get out of a certain kind of liquid? And so as you can see, we put two surfaces very close together. We put the liquid in between, we put voltage on them, and then they try to slam together. So we're measuring the static cling force. This is the math that describes it. As I was saying earlier, this is the spatial derivative of the energy that tells us what the force is. All right, so we can measure the PSI. So for instance, this is pounds per square inch. And in this case, for the red line, this is for Trell stuff that we try, and the green and the blue are what we tried with the vegetable oil. Vacuum is provided as a reference, and that's the cyan line. So one of the big problems for air, which we didn't test because we can't, is air breaks down here. You can't even register the force if you have air. But we were able to get up to 2 psi using this for Trell, which is a very acceptable pressure. And so the animation on this will no longer work, but so now that we have a medium that we know that we can use, instead of thinking magnets going north to south, think charge plus and minus. So negative wants to go to the positive and it repels against the negative. So there was a translational motion issue or picture with the, or animation rather. So, and this is similar. So this is a prototype machine that we built. So instead of windings, we now have all these little pegs, these little pins. And these pins, we can put charge on these pins, put voltage on them, and then they attract and repel each other. And this resides in a housing, and that housing is filled with the liquid. And so this thing is around 8 inches in diameter. So And so this shows you, these diagrams show how we manipulate the colors represent pins of different voltages. And so we manipulate the voltage on these pins to change the electric field and thus pull or push on the rotor as we see fit to get the torque that we want. This is a three-phase machine. This is a single-phase machine. We'll go ahead and skip this math. So this simply describes how we calculate the capacitance between any two given pins. And the derivative of that capacitance with respect to position gives us a function to calculate the torque. And so it gets pretty hairy, but it works. And so here's our traditional magnetic servo motor. This is a dynamometer stand. Here's our motor. This is our first prototype we built. We actually used a glass tank as the frame for it. And then you can see it here in all its glory. And we filled the tank with our liquid to facilitate the electric pressure. This is the capacitance versus position. And so the derivative of these waveforms is what gives us torque. And so this just makes us academics feel happy when our analytical and finite element measured things all overlap. So this is our sort of proud papa moment. And this is our torque that this particular machine made versus our electrical angle that we applied. And they all correlate pretty well. And then this plot here, this is plotting the power that we dissipate versus voltage and electrical angle. And so one of the cool things about electrostatic motors is that you don't have to put electric current through them per se at zero speed. So in an electromagnetic motor, when you're at stall and you want to have torque, let's say you're a robot and you just want to stop and you want to hold something. You have to provide torque force to keep that thing still, right where it is, right? And so you have to continuously pump current through the windings to maintain that torque. Those windings heat up. And so electric motors, traditional ones, do not like standing still because they have no way to cool themselves because they're not spinning, there's no fan to blow air. And so you have to have auxiliary cooling systems to allow them to sit still for long periods of time. Electrostatic motor, the cool thing about that is that you put voltage on something and you're just maintaining a charge. And so it'll just maintain that force. There's very little flow of current, just leakage. And so this is something that we're pursuing further in that we're able to maintain, Newton meters of torque with only having a relatively low amount of watts loss because we're inherently a voltage-based system instead of a current-based system. So our first original prototype motor, percent parts volume and mass. This motor is mainly liquid, which is kind of funny to think about, is that there's a liquid that fills up that motor. And so the liquid takes the place of iron in our motor. Instead of having iron surrounding our windings and magnets, we have liquids surrounding our surfaces. And so this is a torque density that's it's an awesome first step. It's about 1,000 times better than the previous people were able to do in the literature. And this torque here, I should actually say, our torque per volt that we actually do is about 1,000 times better. So we're about in the same ballpark as fractional horsepower induction machines with this very first prototype that we did. So the next part here is instead of having dowel pins pressed into the surfaces, why don't we make a plastic substrate, coat it with metal, and then if you want, you can passivate the surface chemically if you need to with another coating. And then, so why not do this? So we did. So this is a motor that is entirely 3D printed. So we 3D printed, instead of having our dowel pins pressed into circuit boards like we had before, this motor was now 3D printed out of plastic. And then we vapor deposited a seed layer of copper onto the surface and then plated it to put the conductor on here. So there's this motor, this metal is only 1/1000th of an inch thick. But the rest of the motor is entirely plastic. And so this machine here, so this, if you go on IEEE Explorer, I actually need to update this. It is up there, so you can download this on IEEE Explorer if you want everything about this motor. And this motor was able, we did, with the 3D printed plastic motor, we doubled essentially over the pin model. We're now at 0.22 Newton meters per kilogram. Permanent magnet motors for air-cooled consumer applications and light industrial applications are around 0.5 to 1 Newton meters per kilogram. So we're inching up on the PM stuff. And so the other neat thing is these motors are upgradable. I can pull a drain plug, drain the liquid out of that motor, stop it back up, pour in a new liquid that has more pressure capability. And I instantly have a new motor with increased performance. I have an upgradable motor. So if it takes off, someone could market it like the new iPhones and things, like the, you know, we have the iPhone 6, iPhone 7. Drain out the liquid, get the iPhone 7 liquid, you know. All right. So ongoing and future work. So I've shown you mainly single phase motors. We're going to 3-phase. 3-phase gives you better torque, but single phase was a good starting point. And we're also concentrating on better dielectric liquids, using advanced optimization tools to get the absolutely perfect geometric structure for these motors. And then our goal by the end of this project is to hit 1 Newton meter per kilogram torque density. So that would be comparable to your to a higher, on the higher end side of a permanent magnet servo motor or fan motor. That's something you would use in everyday life. But our motor would be made out of plastic. And you can just grind it up and turn it into whatever else you want. So that's the idea. So thank you, and I'll be happy to take any questions. Yeah.
Every speed, torque, efficiency curves.
Yeah, so not on this presentation, but for these types of machines so far, we've been mainly focusing at around 500 RPM as a maximum limit, because they're filled with a liquid. There's a viscous drag loss. So the faster you let it spin, the efficiency just falls. And so one of the things that we're concentrating on is going where electromagnetic machines are typically not as good, which is at near low to zero speed, because the size, like for instance, say you want to make a direct drive wind turbine. They exist, several companies do make them, but they are very, very, very difficult to do, because you have to make mega Newton meters of torque. If you're going to be having a 2, 3, 4, 5 megawatt wind turbine that rotates at 15 RPM or whatever it is, you have to make mega Newton meters at that speed. And so electric machines are sized based on their torque capability. So they get really, really big if you want to keep them efficient. Whereas with this doesn't suffer from the low speed, high current problems of magnetic machinery. So magnetic machines are always going to have the efficiency edge, I would say, in medium to higher speed, no matter what, simply because they're not filled with a liquid, and also just the way the physics works out, you're going to have a better motor for, say, thousands of RPM and higher. For stuff that's going to be going slow or particularly position and hold, like industrial automation, large diameter fans, wind turbines, low speed direct drive, maybe wheel hub motors only go a couple hundred RPM. I think that's where this will have a good advantage, as it's lightweight and it's not current-based torque, it's voltage-based torque. So the I squared R loss is very, very small. These motors are inherently higher voltage. And so for the same reason we push power around in our grid at high voltage, use small conductors, low loss, can't push gigawatts around at low voltage. The conductors would just be astronomical. But same thing applies here. These motors are medium voltage, or you can call them high voltage motors. They operate at thousands of volts. So you can't just plug them in the wall. So there is an electronic interface that has to go between the wall and the motor. But we're working on that. We have prototypes of that. So your microwave oven is, 2.5 kilovolt RMS, around, might be 4 kilovolts peak. Your CRT monitor, if you still have one, those are 20, 30 kilovolts, all the electronics in that. So there are, believe me, this is not ready for prime time today, but it's showing a lot of promise for the future.
You mentioned you looked into the possibility of vegetable oil, and I was wondering, since there's a lot of different seeds, oils from nuts and seeds, and also there's biodiesel, what range of things you looked at in terms of their properties?
Yeah, so let me go back to my, we'll go look at the electrical pressure capability of vegetable oils. So FR3 is a commercially available oil that's used by utilities. It's vegetable oil, but they put additives in it to keep it from going rancid. So if you're going to pour it into a transformer and go have it sit on a pole for 30 years, they had to put a few things into it to keep it from going rancid. But that's actually something that's really cool, is that the utility industry is going to vegetable-based transformer oils in utility transformers and systems, which is pretty cool. They're ester 5 oils. And then this is vegetable oil that's literally came off the shelf from Hy-Vee. So there's the linseed oils, there's sunflower oils, there's a myriad. The thing that oils all have in common is that their permittivities. So this plot here is a normalization of a normalization, but so the relative permittivity of a liquid is a character, it scales the pressure. Oils all are usually around a 3. You have to make the molecules more polar to give them more of a moment to get their permittivity up. And so one of the limitations with oils is, while they provide great breakdown strength, we can get up above, right in here around 15 kilovolts per millimeter. One problem is that their permittivity is relatively low. Some of these other oils, like, or not oils, but this is a dielectric liquid provided by DuPont, and that one has a permittivity of around 7, so twice that of oil. And so there's an entire new area of chemistry that's opened up for this, because normally when you buy an insulating liquid, you don't want permittivity, because permittivity conducts flux lines. And so you want low permittivity, high breakdown strength. And that's something that that usually the people that manufacture these are going for. They're not trying to actually make it with high permittivity. And so that's one of the challenges, but also at the same time an opportunity. Yeah.
So you mentioned applications in direct drive wind turbines. Maybe it's just because I'm not so familiar with electrostatic motors, but does generating power work the same way, or just spinning the opposite direction?
Yeah. So It does work. So what happens is that instead of, it's the direction of motion relative to the direction of the force. So if you have a negative torque and a positive speed, that's negative power, which is the convention we usually assign to generating. If you have positive speed and positive force, then that's positive power. We call that motor. And so there's 4 quadrants. If you have negative speed and negative force, or torque rather, then you have positive power. And so it just depends on which quadrant that you're operating in, whether or not you're a motor or a generator.
If you do a loss budget of your system, it would include the electric drive and compare that to the conventional other motors. How does that compare? And are you looking at resonant power supplies for the drive? When you talk about the iron core transformer and microwave oven, would that be contributing to a large loss of your system?
Good question. So right now, our concentration on the drive aspects are in a couple different areas. So there's a variety of ways to go from 120 volts or 480 volts up to 5 kV or so, which is what you need for one of these. And there's solid state conversion. There's solid state conversion done in conjunction with transformers. So for instance, one of the reasons in a microwave oven's transformer is big and bulky and heavy is that it's designed to just plug in the wall at 60 hertz. If you do a hybrid design where you have a solid state high frequency inverter in front of it, you can shrink that transformer to be a fraction of its size, directly proportional to its frequency. So that's why old aircraft all have, like 400 hertz and things like that, and it makes all their magnetics less weight. But so you can make the transformer quite small and compact, and that's one of the approaches my students are doing. But right now we're looking at, it depends on the size. Usually the smaller power level you are, the lower the efficiency you're going to get. So for instance, a wind turbine's power electronics, I don't know, they're probably around 99% efficient, somewhere in there, at a big utility scale. And then like a motor drive that you'd have, you put on, say, a drill press or something small. You're looking at in the lower 90s. And so that same rule would still apply for this thing. Just the electronics wouldn't, the net energy conversion would still have around about the same efficiency, but the electronics would look much different because there's no step-up functionality in conventional motors. Did I answer your question, or?
So it's the losses in the drive to the motor are similar to the other conventional.
Yeah, they'll be about the same. About the same. The reason that is, although we're doing the extra step-up function, because our current is so low, because we're at higher voltage, the I²R loss of the motor and the filters and other stuff that would otherwise have been there in a lower voltage motor are now gone. And so it's more or less kind of a wash.
Question? What's Vertel? What is that? You let it out in the environment. What would it do?
This, you pour this stuff on the ground and it evaporates pretty quickly. It's a hydrocarbon, and it's made as a replacement. So it was developed for the semiconductor industry. For when in the semiconductor industry, they used to use a lot of acetone to clean everything, whether it's dyes or whatever. And so this was developed by DuPont for the semiconductor industry as a replacement for acetone. So it's non-flammable. That was the main one. So it can't burn. This is not something that I think will be a long-term solution at all, because it's rather expensive. But the neat thing about this is that I have colleagues and also I have a startup that's working on this, I should say, that this has been left behind. So organic things that you can ingest even if you wanted to are really the kind of the route we're trying to pursue. I mean, this has an MSDS of 101, but we're essentially moving forward with stuff you could hopefully eat.
Thank you for your presentation today.
Thank you.